Thank you, viewers. This is Mr. Dingo. Welcome once more to a lesson on applications of differentiation. In our class, we talked about application of differentiation on kinematics. In this lesson of today, we are going to look at application of differentiation on mensuration, or in other words, measurements. And the first part of this application area will be on perimeter and area. And without wasting time, let's go to the first example, which is a farmer has 280 meters of wire mesh to enclose a rectangular garden. Determine the maximum area you can enclose with the 280 meters of the wire mesh. So the first thing I do is to sketch that rectangular garden and see this rectangular garden. I'll say let me have length as x and width as y. So from perimeter, we know that this 280 worth of wire mesh is what is going to cover this distance. So in other words, this is our perimeter. So if this is our perimeter, we are going to have, we know perimeter equals to 2 into length plus width. And in this case, our length is x, so I'll say perimeter. And our perimeter, let me just substitute, is 280. So 280 equals to 2 into length is x plus width is y. So 280 equals 2x plus 2y. Let me divide each term by 2. So I'll get 240 equals x plus y. Let us make y the subject of formula. In this case, we can make y, but in this case I want to deal with y. So y will be 140 minus x. Once I have this one, equation 1, as the value of y, let me now get area. And in this case, we know area equals to length times width. And in this case, my length is x and my width is y. So area is x, y meters squared. Now with that area, if I take this value of y and then I substitute where y is here, what will I have? We'll get area equals to x into 140 minus x, because that is our new value of y. If you open that bracket, we'll get 140x minus x squared. So if we have, this is the area of the enclosure, and we want to be able to determine whether what is the value of x that will give us the maximum value of area, because we need the maximum area enclosed. And you know that at maximum area, or at maximum turning points, dA dx will be 0. So let me say dA dx here will be 140 minus 2x. And this 140 minus 2x, it should be equal to 0 at a turning point, meaning either a minimum or at maximum turning point. So with this, we'll take 2x here equals 140. So over 2, x is 70 here. Now this 70 meters should be the value of our length here. The value of our y, we know y we said is 140 minus x. So we'll say y here is 140 minus 70, which is also 70 meters. So what we said was a rectangular garden actually is a square garden, because the length is 70 meters and the width is also 70 meters. So the area itself, area here, we know that is length times width, the way we got here, x times y, so it will be 70 times 70. So the area is 400, that is 4900, that is 4,900 meters squared. So, but how do we determine that this is maximum area? We have to use the neighborhood test to be able to confirm that. In the neighborhood test, we use 3 rows. This is x, this is dA dx, this is shape. And in this case, we are going to have 3 other columns. These 3 columns, this is x is 70 when dA dx is 0. So let me put 70 here. A number more than 70 could be 71. A number less than 7 could be 69. We know that here is 0. So if we substitute this 69 in the derivative, which is 140, 140 minus 2 into 69, we'll get positive 2. This is positive 2. And then what about if it is 71 to 140 minus 2 into 71? That is negative 2. This is negative 2 here. So the shape here will be that. Here is flat and then here is dropping. So we see that the gradient is changing from positive, 0, negative. And we said earlier that if you see that kind of change, then that turning point is the maximum turning point. So in other words, this area we have calculated using the value of x as 70 is our maximum area. I said earlier also we can use second derivative, that is d squared a over dx squared equals, if you differentiate this one once more, you are going to get negative 2. So we said that if this one is d squared a or dx squared is greater than or is less than 0, if it's less than 0, then that one is a maximum turning point. So you have your neighborhood test, you can confirm, and you can also use the second derivative to be able to confirm that. But in your exams, this is what is mostly required of you. Let's go to example 2, which is a farmer fences a rectangular garden on 3 sides. And the house forms the 4th side of the garden. Find the maximum area you can fence with 80 meters of fence. Now, this is a very practical case of our traditional farming in Africa, especially small gardens behind the house at home. You realize that they are put that way so that at least we don't use a lot of fencing material on the farm, so that the house, being already an erected barrier, forms part of the fence. So it means the fencing material, which is 80 meters here, will only form these 3 sides. So the first thing, like in example 1, what we looked at first is we apply perimeter. But in this case, we are going to deal with the side which is fenced. That is 80 meters will be x plus y plus x. Let me say x plus y plus x should give us 80 meters. And therefore 2y plus 2x equals to 80 meters. So y here will be 80 minus 2x. So again, like I said before, what is the area of the farm? The area of the farm here should be x times y. So let's say area is equals to x, y. But our y is here, so we can substitute where y is. That will be area equals to x into 80 minus 2x. So area, if you open the bracket, will be 80x minus 2x squared. But we also know that at maximum area, or in other words, at turning points, whether minimum or maximum, we know the dA over dx will be 0. So here we say at that one dA dx will be 80 minus 4x. But we know that at maximum area, this one equals to 0. So I say at maximum, that one dA dx will be 80 minus 4x equals 0. So 4x here equals to 80 over 4, x should be 20 meters. So if the value of x is 20 meters, but y is 80 minus 2x, so y will be 80 minus 2 times 20, that is 80 minus 40, which is 40 meters. So we have the dimensions of the farm or the garden, which is x 20 meters by 40 meters. It means that the area of this farm will be length times width, which is xy, so that is 20 times 40. That will be 800 meters squared. Now we have the area, but like I said, sometimes you need to confirm whether the area you have is minimum or maximum. To do so, we need to actually use the value of x in the neighborhood test, whether we confirm if this is x, this is dA dx, this is shape. We then have this is 20, and we know this should be 19, this should be 21. So we know this is 0. We'll substitute 19 in our dy dx, which is 80 minus 4x. So if I say 80 minus 4 times 19, I get 4 positive. And if I substitute 21, that is 80 minus 4 times 21, I get negative 4. So we say that a positive gradient slopes like that. A 0 is a horizontal line, and a negative slopes negative like that. So we know that if the gradient changes from positive 0 then negative, that is a maximum turning point. So we can therefore know that the area calculated from 20 here should be maximum area. So if you want to get the maximum area of this garden, where we are going to use all the 80 meters of fencing material without even a piece remaining, we need to measure out 40 meters by 20 meters of this garden, and therefore the area we are going to enclose will be 800 meters square. And I also said another way of confirming whether it's a maximum is using the second derivative, which is d squared a over dx squared should be, if you differentiate the gradient again, which is this one, we are going to get negative 4. So we said that if the second derivative is less than 0, that means the maximum turning point. So our case here we have negative 4, which is less than 0. So it is a maximum area that we have calculated. Let's go to example 3. Okay, this is our example 3, and it reads: the shape of a flower garden is in the form of a large rectangle partitioned by parallel lengths of wire mesh into 12 equal smaller rectangles. This is the farm. We can see the bigger farm is a rectangle, but it is also divided into other 12 smaller pieces, 1, 2, 3, 4, 5, 6 times 2. So those are 12 pieces. We can see that we have been told that these smaller rectangles are equal in size. So we know that one of them, the length is x and the width is y here. We are told to show that the total area enclosed is A equals to 1296 x minus 108 over 7x squared, and find the maximum area which can be enclosed in meters squared if the total length of fencing material is 12 meters. So we have 12 meters, that is the total fencing material, meaning all the material used to divide this thing, the way we can see it, it is 12 meters total. So let us start by showing that if we need the total of this length, then we know that it must be, we know x is here, this is x, another x, x, there's another x here. So we have how many x's? We have 1, 2, 3, 4, 5, 6 times 3, because there's this one, this and that. So it means we have 18 x's. So we are going to have 18 x plus, let's go to y. This is y here, y, other y. All of these ones, the vertical lengths are y's. And how many are they? These y's, if you look at here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So plus 14y, we should get 15, 12, because that's the total length of the fencing material. So if I make y the subject, I'll say 14y equals to 15, 12 minus 18x. Y here will be 15, 12 minus 18, x divided by 14. Divide by 14. So y equals, if I try to divide by 2, 15, 12, divided by 2, will be 756 minus 9x over 7. So we have y equals to 756 minus 9x over 7. That's the value of y. Let us now substitute this y to get area. The area of this fence here, if we have this y that we have here, what do we have? We are going to get the area of this small rectangle. So we'll say area of the small rectangle will be length times width, and area is xy. So we know that if xy, let's substitute y here, so we'll get x into 756 minus 9x over 7 here. So if you open this bracket, area will be 756x minus 9x squared over 7. So that is what we have as area. The area that we have here now is the area of the one small rectangle. Now we know that the total area that we are told here is this small rectangle times 12, because there are 12 small rectangles here. So we'll say the total area therefore will be 12 into 756 minus 9x squared over 7, like that. So if you open that bracket, we'll be able to get area equals, let me get some space up here so that we can continue. So the area here, if I open that, will be A equals, if I have 12 times 756 is 9072x minus 12 times 9 is 108 x squared. We know that everything here is over 7. But now we realize that the expression of the function we are given here is, there's no 7 here. It means that let us simplify each term by 7. So we are going to have 9072 divided by 7 is 1296. So 1296 x minus 108 x squared over 7. So we have reached the point here. They have told us to show that the total area of this enclosure is our area equals to 1296x minus 180 over 7 x squared. We have it there. Then the second part of the question is find the maximum area which can be enclosed in meters squared if the total length is that. So if we want to get the maximum area, we know that we have to differentiate dA dx equals 1296 minus 108 times 2, that is 216 x over 7. But we know that at this particular point, this one is equals to 0. So what we can say therefore here is 216x over 7 equals 1296. We get over 1, so we'll get 216x equals, you multiply this by this, you'll get 9072 over 216 divided by 216, we'll get x equals, so 9072 divided by 216, we get 42 meters. So the length, the value of x for the one small rectangle here is 42 meters. Let's get the y, where we know y, we already got the expression here for the function here for y, which is y is 756 minus 9x divided by 7. So if you are to get the value, of y, you'll say y equals to 756 minus 9 times 42, everything divided by 7. So we divide this one, we get 54 meters. So 54 meters is the length that we have. So we can say this is y, that is x. So if we need to get the maximum area that we are told to get in this case, is to simply, we know that this is the length of the small rectangle, this is the length of the small rectangle, the width of the small rectangle, but we know there are 12 small rectangles. So we'll say the total area here will be 12 into 54 times 42. So that will be, if I have that, 12 into 54 times 42, I get 27 to 16 meters squared. We know that, why am I putting this in bracket? This is the area of the small rectangle, but we know there are 12 such rectangles here. That is why we have that. But if you are to confirm whether this is maximum or minimum turning point, what do the minimum or maximum area that we have got? We need to go for a neighborhood test, where we are going to use the value of x to test. So this is x, this is d, a, dx, this is shape. So if I have this the way they are here, this is 42, let me say this is 43, this is 41. We know this is 0. So at this 41, let me substitute our dA dx is up here. So let us substitute, that is 216 times 41 divided by 7, then 1296 minus answer is positive 30.9. If I round out to one decimal place, then if I say 216 times 43 divided by 7, so 1296 minus answer, I get negative 30.9 if I round out one decimal place. So the gradient here is vertical or slanting positively. This is horizontal, and then that is that. So we can confirm that the gradient is changing from positive 0 to negative. That is a maximum turning point. So it means that the area we have got here is actually the maximum area. Now we want to look at application of differentiation on surface area and volume, and previously we have looked at the applications of differentiation on perimeter and area. So we want to go to part B, which is looking at surface area and volume. And here we have a question 1, example 1, which is saying a large tank is in the shape of a cuboid. A large tank in the shape of a cuboid is to be made from 54 meters square of metal sheet. The tank is open at the top. So if this is the tank, it means at this top here there's no cover. The height of the tank is x meters. We can see that. The two opposite faces are squares. This is this face here, and the other face here are squares. Then use differentiation to find the maximum volume of the cuboid and justify the volume is maximum. So what we need to do first of all is to express equation in terms of surface area. We know that we can get the surface area of this cuboid, or we can get the function to that effect. We know that this face here, the area of this face here is xy, and this face here, there are three of them. There is this one, there is the bottom face, and then there is the other face on the other side, but there's the top is missing. So I can say the first one xy here, this other one is xy, this is also xy. So I'll say xy plus xy plus xy, that is the three rectangular faces. Now there are two square faces, x squared and x squared. So I can say plus x squared plus another x squared should give us the surface area, which is 54 meters squared. Now 54 centimeters squared, let's use centimeters squared, so this is centimeters squared. So if we add this, this will be 3xy plus 2x squared should give us 54 meters squared there. And I want to make x the subject, so I'll say 3xy equals to 54 minus 2x squared. If I divide everything here by 3x over 3x, I will get y equals, well, let me just say 54 first, minus 2x squared over 3x. That is what we have as y. So when we have this one as y, and we need to get the volume of this cuboid, volume V. Volume is length times width times height, and we know that in this case length is given as y, so we'll say y times x times x, that will give us volume. So V here equals to, let me x squared y. So x squared y, but y is down here, so I'll say V equals to x squared into 54 minus 2x squared over 3x. Opening bracket, we'll say this is 54x squared minus 2x power 4 divided by 3x. So now I can simplify. 54x goes there, x, this is 18x. So 18x minus x goes there, x power 3, but this will be just 2 over 3. So we have the expression for the volume is 18x minus 2 over 3x cubed. But now at maximum volume here, dV dx equals 18 minus 3 coming here will be 2x power 2. Because if I bring 3 here, 3 times 2 over 3, 3 and 3 will cancel, having 2x power 2. We know that at maximum volume, at a turning point, this one dV dx must be 0. So we have 2x squared equals 18. If I divide by 2, x squared is 9. If I get square root here, square root of a positive number should either be x equals to 3 or x equals negative 3. But we know x should be length, and if x is length, it means that x negative 3 is not going to be used for this calculation. So we can say in this case here that the value of x for our example here is 3 centimeters. Now, will these 3 centimeters give us maximum volume or minimum volume? We can test that using neighborhood test, which is x dv dx, and this is shape. So if you do that, this is 3, let me say 2, 4 here, this is 0. So if I substitute that one in the gradient here, that is 18 minus 2 into 2 squared, I get 10 positive. And if I put 18 minus 2 into 4 squared, I get negative 14. So it means that here the positive gradient is that, this is this, and that is that. So if the gradient turns from positive 0 to negative, that means that the value of x here will give us maximum volume. So for us now to get the volume itself, the volume maximum that we need, we are just going to substitute in this is the function for the volume. Volume was equals to 18x minus 2 over 3x cubed. That's the volume. So let us substitute the value of x, which is 3. That is 18 into 3 minus 2 over 3 into 3 cubed. This is 54 minus, we have 27, that's 27, 3 cubed. 27 times 2 divided by 3 is 18. So 54 minus answer is 36. So the maximum volume here is 36 centimeters cubed. That is the maximum volume. 36 centimeters cubed. Now, that is the answer that we can get from this particular case here. So you realize that in this case, what I've done here is we were given surface area in the equation 54. The metallic sheet that was used to make this metallic tank was 54 centimeters squared. So I have to develop the formula for the function in terms of surface area to be able to eliminate one unknown to get that one, and then use that one unknown, substitute in the volume now to be able to get the volume function, then differentiate. Sometimes you may be given volume. If you're given volume, you have to start by using the volume function, then you transfer into surface area. So that will depend on what is provided for you. Let us go to example 2. Okay, now we have example 2, which is an open box. Is made up from a thin sheet of metal measuring 10 centimeters by 10 centimeters. 4 squares of side X are cut away and the remaining 4 sides are folded upwards to make an open box of depth X centimeters. Calculate the maximum volume of the box and state its dimensions. Now, this information here may not make a lot of sense until we make sense out of it. We know that let's sketch a square box the way they have told us, 10 by 10. So if you have this is a plain sheet. We have not made a box yet. It's a plain sheet, a square, which is 10 and 10 centimeters each. But we know for us to make a box out of this one, we have told that this is what welders do. They cut some small boxes at the corners. So if we cut these small boxes at the corner, these are the corners, they're talking X here. So if you cut this one here out, and you cut this one also out, and you cut this one out, and you cut that one out, what is going to happen is that we know that this is X, this is X, this is X, this is X, X, X. If you cut these ones away, like they have told us, what remains is something of this nature. But we know that if this is X and this is X, it means that this one here should be 10 minus 2X centimeters. This part here, the same to this other side, 10 minus 2X. So if you fold this part and you fold this part and you fold this one and you fold this one, we are going to have a box of this nature. We are going to have a box here, and this is our box. And in this box here, this height, once you fold this part here, this X becomes the height. It means that this one is going to be our X centimeters. But this part here will be our length, which is 10 minus 2X. But because it was a square, they are the same. So 10 minus 2X here. It means therefore that we can be able to get the function of the volume. And in this case, we can now move to get the volume of this box. And the volume of this box here is volume equals to length times width times height. And the volume we have will be length, there is 10 minus 2x times 10 minus 2x times x. Okay, so let us open the bracket. I will multiply x by this so that I get v equals to 10x minus 2x squared times 10 minus 2x. What I've done here is I've taken x, multiply, I open this bracket. So I have 10x minus 2x squared, then I multiply by this one. Again, I have to open the bracket by saying 10x into 10 minus 2x minus 2x squared into 10 minus 2x. So if you open this one, we'll get 100x and then minus 20x squared minus 20x squared plus 4x cubed. This one is v. So if you collect like terms, I can say v therefore equals to 4x cubed minus 40x squared plus 100x. This is the expression for volume. Now, at maximum volume, because we have been told to get maximum volume, at maximum volume, dv dx equals 0. So let me say dv dx equals, this is 12x squared minus 80x plus 100. This one equals to 0 at maximum volume. So I want to divide this one by simplify by dividing by let me say 4. So 4 here, 4 there, 4 there, 4 there. So this will be 3x squared minus 20x plus 25 equals 0. So that is what we have. So if I look for two numbers that if I multiply I get 3 times 25 is 75, and if I add I get negative 20. Those numbers I bet should be both negatives. Negative. So let me see there. Product is 20. Product is 75. And sum is negative 20. So negative 15, negative 5. Negative 15, negative 5, yes. So we'll say this is 3x squared minus 15x minus 5x plus 25 equals to 0. So this will be 3x into x minus 5 minus 5 into x minus 5 equals to 0. So 3x minus 5 into x minus 5 equals to 0. So x here equals 5 over 3, or x equals 5. Now we have two values of x here, but we don't know which value of x will give us maximum volume. So first we have to go to the neighborhood test to be able to tell us which of these values gives us maximum volume. Is it 5 or is it this one? But we can just test one. If we test one, we can be able to know. So let me take the smaller one, which is 5 over 3. Usually students will be quick to run to 5 because they think 5 is bigger. But that is not the case always. Be careful to ensure that you have to confirm. Let us see what is going to happen. And this is x dv dx, and this is shape. So this is 5 over 3, which I know the gradient will be 0 already. Now smaller than that, that's like 1, so I'll say 1. Then this is 2. So if I substitute this 1 in this expression here, where is the, this is my gradient, 12 into 1 squared minus 80 into 1 plus 100. I get positive 32. And if I substitute 2, get 12 into 2 squared minus 80 into 2 plus 100, I get minus 12. So viewers, you see what I was talking about here. Mostly I've seen students rushing to take the bigger value because they think the bigger value will give them the maximum volume. But that's not the case here. I want you to see that if you have 2x, if x is 5, so you take 5 times 2 here, meaning this part will be 5, 5, and then this is 5. So you have like a cube and a cuboid. You realize that if you get the volume of that cube and then you look at the volume of the cuboid we are going to get when you get this, you will get this one, you will get more volume, a bigger volume than the other one. So that is something you have to really think about. So here is going to be that way. So we can actually tell that this value here will give us a maximum volume, not this one. So we are going to now get the volume using the value of x here, and our volume in this case was here. Volume equals to 4x cubed minus 40x plus 40x squared plus 100x. Our x is 5 over 3. So I'll say 4 into 5 over 3 cubed minus 40 into 5 over 3 squared plus 100 into 5 over 3. So volume here will be, let me see, 5 over 3 cubed times 4. That should be 500 over 27 minus 5 over 3 squared times 40. That gives us 1000 over 9 plus this 500 over 3. So if I add these other ones, all of them, 500 over 27 minus 1000 divided by 9 plus 500 divided by 3, I get 200 over 27. This is volume is 200 over 27 centimeters cubed, or you can say 74 and 2 over 27 centimeters cubed. That is the maximum volume. But viewers, we also told to get the dimensions. The dimensions are much more easier because the dimensions are here. So what we are supposed to do with these dimensions that will give us maximum volume is to be able to just substitute these dimensions. So we have, we know first length, let me say length, it will be 10 minus 2x, and 10 minus 10 minus 2 into 5 over 3, that gives me 6 and 2 over 3 centimeters. I know that width is the same because width is also 10 minus 2x, so that will also be 6 and 2 over 3. But we know height already is x itself, and x is 5. X is 5 over 3, which is the same as 1 and 2 over 3 centimeters. So these are the dimensions of this cuboid that we have. If you multiply this by this by this, I bet you will get here. Let's see. 6 times 6 is 36. 36. 2 over 3 is almost 6.67. Let me try. 6.667 squared times 1.667. 74.09, almost close to that. So that is our answer. So I believe you are following these ideas. Let us go to example 3, which is the final example in this particular chapter. Okay, we have example 3 here, which is our last example for this particular chapter. We have the question says a closed cylindrical metal tin is to have a capacity of 250 pi centimeters cubed. If the surface area of the metal tin is to be minimum, what would be the radius of the tin? So we know what a cylinder is. In this case that we have now, the first function will be in terms of volume, because that's what we have here. This cylindrical container here, the volume that it should carry should be 250 pi centimeters cubed. That's what the volume should be. So we want to know if the surface area that we need to, of the material we should use here should be very minimum, the least, to give us this volume here, then what is the radius of this tin that we should cut? So the first thing we need to do is what's the formula for volume? The formula for volume of a cylinder is a pi r squared times height. This is our height here, this is our radius here. Radius is there. So if this is the volume, so I can say therefore pi r squared h equals to volume, which is 250 pi. 250 pi. I can remove, let me make h the subject, because I want to remove h so that I remain with only one unknown in this case, which is r. So I'll say divide by pi r squared, divide by pi r squared. So in this case, pi and pi, r and r squared will go, so h equals to 250 pi over pi r squared. But we know that pi and pi will also cancel, so the h here is 250 over r squared. This is the value of h of that particular tin. Now we need to, after getting this h here, we need to now bring in the surface area of this tin. The surface area, we know that this container here, we know is closed. So if it is closed, meaning this top circular part is there and this top circular part here, it means that we're going to have pi r squared plus pi r squared. That is going to be 2 pi r squared for the top and the bottom. Then plus the curved surface. The curved surface will be 2 pi r h or pi d h. That's the curved surface area. So this is the total surface area of this particular cylinder. But we know that in this case, our h is here. So where h is, we are going to be able to substitute that one. So I'll say surface area, let me just say area, equals to 2 pi r squared plus 2 pi r times 250 over r squared. That will be a equals to 2 pi r squared plus, this is 250 times 2 is 500, 500 pi, then r and r, that will be over r. So that's what we have. Now we know that at minimum surface area or at minimum area, dA over dr should be dr should be 0. So let's differentiate. That will be 4 pi r plus. You realize that what do we need to do here? First, let me show you something here. If we have this 500 pi over r, we know we have to bring this r here. So if you get the reciprocal of r, it will be 500 pi r minus -1. So before I go to differentiate it, let me first of all express it that way, so that we have 2 pi r squared plus 500 pi r minus 1, because we cannot differentiate when it's a fraction this way. So dA dr will be 4 pi r plus, now minus, because negative comes here, so it will be minus 500 pi r minus 2, because if we subtract 1 here, it will be negative 2. We know that this one should be equal to 0 at minimum point. So at minimum point, let us say, now let me say 500, let me say 4 pi r equals positive 500 pi r minus negative 2. We know that we can divide both sides by pi, so pi and pi will go. That is 4r equals to 500r negative 2. But I know what I did here, I can do it again by now removing this one as a negative and bringing as a fraction, meaning reciprocal of this. I'll say 4r equals to 500 divided by positive r squared. I've just be able to get the reciprocal. I know that if I have r raised to power negative 2, I can say that's the same as 1 over r raised to power 2 positive. And if I open this, that will be 1 squared over r squared, which is the same as 1 over r squared. So that's exactly what we are going to get. Then we cross multiply, we get 4r cubed equals to 500. And r cubed here will be 500 divided by 4. R cubed equals, so 500 divided by 4 is like 125. Divided by 4, 125. If I get cube root of both sides, I'll get r equals to 5. So our r is 5. How do we know that it's going to give us the minimum area? We have to use neighborhood test to confirm that the area we are going to get, if radius is 5, will be minimum. So this is r, this is dA dr, this is shape. So this is, we divide in 3 columns. This is 5, let me say 4, 6. So this one we are going to substitute in the derivative, which is here. So what I'm going to do here is 2 pi, 2 times pi, which is, no here, sorry, that is 4 pi, 4 times shift, pi is there, times r, and our r is 4 minus 500 pi times r, which is 4 power negative 2. That's giving me negative 47.9. If I round off to 1 decimal place, we know here is 0. What about if it is 6? It's going to be 4 shift pi times 6 minus 500 shift pi into r is 6 power negative 2. That is 31 positive 31.8, correct, to 1 decimal place. So you see that there the line is negative, so it means the line will go this way, the 0 will go this way, positive goes that way. So you realize that when the gradient turns from negative 0 then positive, that is a minimum turning point. So we are sure that our r here, our r, which is radius, will give us the minimum surface area of this particular tin. Thank you, viewers. That's the end of this chapter of differentiation, and please be sure to subscribe to our channel so that you support us, so that we are able to continue providing these very important lessons during this time of coronavirus crisis. Thank you very much.